Light is the fastest thing in the universe. Nothing outruns it. Nothing even comes close. A single photon leaves a flashlight in your hand and reaches the wall across the room in 10 billionths of a second. That same photon, fired horizontally across the surface of the Earth, would lap the entire planet 7.5 times before a single second had passed. In the time it takes your brain to register the sensation of touching a hot stove, light has already traveled from New York to Los Angeles and back, roughly 10 times. We built our intuitions around this speed. We say light speed to mean instant. We say at the speed of light to mean as fast as anything can possibly be. The phrase carries a kind of finality, a sense of arrival at the ceiling of what the universe allows. And, for most of human history, even the question of whether light had a speed at all was considered unanswerable. Ancient philosophers debated it earnestly. Aristotle believed light was instantaneous. Descartes agreed. Even Kepler, who mapped the orbits of planets with extraordinary precision, assumed that light simply appeared everywhere at once, that it was not a thing traveling through space, but a condition, a state, something that simply was. And tonight, quietly, gently, we are going to dismantle every comfortable assumption that surrounds this speed. Because here is the truth that sits at the center of everything we will explore together in the hours ahead. The speed of light is not fast, not where it matters, not at the scale the universe actually operates on. The speed of light is, in the only sense that counts across the cosmos, agonizingly, almost unbearably slow. So slow that a photon fired toward the nearest star beyond our sun will not arrive for 4 years and 3 months. So slow that a message sent at light speed to the most promising nearby system, where astronomers suspect a world capable of harboring life, would not arrive until your children are adults. And any reply would not return until they are old. So slow that a civilization 1,000,000 years more advanced than ours, building spacecraft with technologies we cannot imagine, would still need centuries or millennia to physically cross the distances between most star systems. The speed of light is not a highway to the stars. It is the wall that keeps everything separated. But we are getting ahead of ourselves. We are moving too fast, which, given tonight's subject, carries a certain irony. Settle in. Let the weight of wherever you are pressing into you now, the mattress beneath you, the pillow against your face, the quiet of the room. There are no advertisements in this video. There is nowhere you need to be. What follows is a long, slow, careful look at the most beautiful and most devastating number in physics. A number that simultaneously reveals the universe to us and seals us inside our own small corner of it. We begin not with the stars, but with something closer, something almost ordinary. The first person to seriously measure the speed of light was not a physicist with a laboratory. He was an astronomer watching the moons of Jupiter. In 1676, a Danish astronomer named Ole Rømer noticed something strange in his observations of Io, one of Jupiter's large moons. Io orbits Jupiter with extraordinary regularity, vanishing behind the planet and reappearing on a schedule so precise it was being used as a kind of cosmic clock by navigators trying to determine their longitude at sea. But Rømer noticed that the timing of Io's appearances was not perfectly constant. When Earth was moving toward Jupiter in its orbit, the eclipses happened slightly earlier than predicted. When Earth was moving away, they happened slightly later. The discrepancy was small but consistent. It accumulated to a difference of roughly 22 minutes over the course of 6 months. Rømer understood what was happening. The difference was caused by light needing extra time to cross the changing distance between Earth and Jupiter. When Earth was farther away, the light carrying the news of Io's emergence had more distance to cover. When Earth was closer, less. The speed of light was finite, it was measurable, and it was, by any human standard, extraordinary. When the Dutch physicist Christian Huygens used Romer's data to calculate a numerical value, the result was roughly 220,000 kilometers per second. Not quite right. The correct answer is 299,792, but staggeringly close for an observation made with 17th century instruments, watching a distant moon from a moving planet. It shattered the idea of instantaneous illumination. Light was fast, unimaginably fast, but it was not infinite. Modern instruments have refined that measurement to extraordinary precision. Light travels at exactly 299,792.458 kilometers per second in a vacuum. Scientists know this number so precisely that they have used it to redefine the meter itself. 1 meter is now officially defined as the distance light travels in 1,299,792,458th of a second. The speed of light is not merely measured, it is the ruler against which all other measurements are made. It is the standard by which the universe is calibrated. On the scale of everyday experience, this speed is overwhelming. Consider the room you are in right now. If you could somehow fire a beam of light from one wall to the other, the round trip would happen so quickly that no instrument your body possesses could detect the delay. The beam would leave, cross the room, bounce back, and return before a single neuron in your brain had time to fire in response. Now extend that beam outward, past the window, up through the atmosphere, into space. The moon hangs in the sky roughly 384,000 kilometers from Earth. Light crosses that gap in 1.3 seconds. When the Apollo astronauts spoke to mission control from the lunar surface, their words traveled as radio waves at light speed across that 250,000-mile gap, and the delay, 1.3 seconds each way, was barely noticeable. A conversational pause, nothing that would suggest the signal had just crossed the most distant terrain any human being had ever stood upon. Now, extend the beam further. To the Sun. Our star sits approximately 150 million kilometers away. Light covers this distance in 8 minutes and 20 seconds. When you step outside on a clear morning and feel warmth arrive on the surface of your skin, those photons left the surface of the Sun before you began your morning routine. The Sun you see hanging in the sky is not the Sun as it exists right now. It is the Sun as it existed 8 minutes and 20 seconds ago. If the Sun were to vanish at this exact moment, if it were to simply cease to exist between one heartbeat and the next, you would continue to see it shining. You would feel its warmth. The birds would keep singing in sunlit air. The shadows on the ground would hold their familiar shapes. And then, 8 minutes later, everything would go dark at once. You would have been watching a ghost. For 8 full minutes, you would have been warmed and lit by a star that no longer existed. 8 minutes is a trivial delay by any human standard. We wait longer for coffee. We wait longer for a reply to a text message. The mind does not register 8 minutes as a meaningful gap. It feels like nothing. A rounding error in the experience of a day. And that feeling, that comfortable numbness to the delay, that willingness to treat 8 minutes as effectively 0, is precisely the illusion we need to crack open before we can understand what the speed of light actually means for the question of whether we are alone in this universe. Because 8 minutes is just the beginning. 8 minutes is the neighbor's porch light. The real distances, the distances between stars, between the worlds where life might exist, between the civilizations that might be looking back at us right now from the far side of the galaxy, those distances make 8 minutes look like a heartbeat. Mars, at its closest approach, sits roughly 54 million kilometers from Earth. Light reaches it in about 3 minutes. At its farthest, when Mars and Earth are on opposite sides of the Sun, the distance swells to nearly 400 million kilometers, and light needs roughly 22 minutes. NASA mission controllers already feel this delay in practical terms. When the Perseverance rover encounters an obstacle on the Martian surface, the signal reporting the problem takes minutes to arrive at Earth. The command to stop takes minutes to travel back. In the intervening time, the rover has been making its own decisions in the dark, navigating by its onboard systems, unable to wait for guidance from human minds 400 million kilometers away. Even at the speed of light, Mars is far enough that real-time communication is impossible. Jupiter lies roughly 778 million kilometers from the Sun. Light needs about 43 minutes to make the trip from Earth. Saturn, 1.4 billion kilometers away, requires 79 minutes. By the time you reach Neptune, the outermost major planet at roughly 4.5 billion kilometers, light requires over 4 hours to arrive. Let us follow one final signal to the most distant object humanity has ever launched. Voyager 1 left Earth on September 5, 1977. It carried a golden record etched with sounds and images of human civilization. The calls of humpback whales, the opening bars of Bach, a spoken greeting in 55 languages, the coordinates of our home star pressed into gold, a message in a bottle launched into an ocean with no visible shore. In the 47 years since its departure, Voyager 1 has traveled approximately 24 billion kilometers. It is the most distant human-made object in existence. It has crossed what scientists call the heliopause, the boundary where the Sun's solar wind finally loses its battle, against the interstellar medium, the point where our star's influence fades and true interstellar space begins. A signal from Voyager 1, traveling at the speed of light, takes approximately 22 hours to reach us, nearly a full day. For a signal moving at the fastest speed the universe allows, 22 hours for the most distant object humanity has ever placed in space, an object that has been flying continuously for nearly half a century. Now, the nearest star. Alpha Centauri is a triple star system. The closest of its 3 components, Proxima Centauri, sits approximately 4.24 light-years from Earth. That is the distance light itself travels in 4 years, 3 months, and some days of continuous motion at 670 million miles per hour, never stopping, never slowing, crossing the void without rest. In kilometers, that distance is approximately 40 trillion. In miles, roughly 25 trillion. Voyager 1, in 47 years of non-stop travel, has covered about 24 billion kilometers. Against the 40 trillion kilometers to Proxima Centauri, Voyager has completed about 0.06% of the journey. If it were aimed directly at that star, which it is not, it would arrive in approximately 75,000 years. Not 75,000 days. Not 75,000 months. 75,000 years. The entirety of what we call human civilization, from the first agricultural villages to the particle accelerators and orbital telescopes, fits comfortably inside a period of roughly 10 to 12,000 years. Voyager would need to fly for 6 or 7 times that entire span just to reach the next star over. The woolly mammoth was still alive when we would need to have launched Voyager if we wanted it to arrive at Proxima Centauri today. This is where we are. This is the real map. And Proxima Centauri is the closest star, the nearest point on a map that stretches 100,000 light-years across its visible disk. A map on which the gap between most star systems is measured not in 4 light-years, but in tens, hundreds, or thousands of them. A map on which the distances are not exceptions. They are the rule. The speed of light is 299,792 kilometers per second. It is the fastest anything in this universe can travel. It is so fast that it defines the meter, calibrates our instruments, and outpaces every other physical process we have ever measured. And it is nowhere near fast enough to make the cosmos feel small. Breathe slowly. Feel the room around you. The stillness is real. The silence is real. What we are building tonight is not fear. It is perspective. A very quiet, very large, very honest picture of the place we find ourselves in. The numbers get larger from here. But so does the beauty. And somewhere inside the beauty, there is an answer to a question a physicist named Enrico Fermi asked over lunch in 1950, in a way that has not let go of science since. A question we will arrive at slowly, gently, the way starlight arrives after its long journey through the dark. We are not ready for that answer yet. First, we need to understand the distances, the real distances, not the comfortable 8 minutes to the sun, but the kind that dwarf everything our civilization has ever built or done or imagined. Let us step quietly into the numbers. Part 2. The real numbers. The light year is the basic unit of interstellar measurement, not a unit of time, though the name suggests it, a unit of distance. The distance light travels in 1 year of continuous motion, at 670 million miles per hour, running without pause for 365 days. A single photon covers approximately 9.46 trillion kilometers. That number, written in full, requires 13 digits. And it is the smallest meaningful increment when talking about the spaces between stars, the centimeter ruler of the cosmos. Think of it this way. Imagine shrinking the entire solar system, the Sun, all 8 planets, the asteroid belt, the distant Kuiper belt, to the size of a coffee cup. On that scale, Proxima Centauri, the nearest star, would be sitting on a table in another city. Not across the room, not down the hall, another city, and the nearest star is the close one. Proxima Centauri, 4.24 light-years, roughly 40 trillion kilometers. Barnard's star, the next, nearest single star to our Sun, 5.96 light-years. In 2024, astronomers confirmed the presence of at least one planet in orbit around it. A cold, dim world that likely resembles a larger, frozen version of Earth. Its surface locked in perpetual chill, its sky lit only by the faint red ember of a dim, red dwarf star. Not a promising candidate for life as we know it, but a world, nonetheless, waiting in the dark 6 light-years away. Wolf 359, 7.9 light-years. A red dwarf so faint it produces less than 0.1% of the Sun's luminosity. Any planet warm enough for liquid water would need to orbit so close that tidal forces would lock it in place, one face permanently baking, one face permanently frozen. Sirius, 8.6 light-years, the brightest star in the night sky. A blue-white star roughly twice the mass of our Sun, burning hotter and faster, and fated to exhaust its fuel far sooner than our more modest star. A beautiful, blazing, probably lifeless system. Its radiation, environment likely too harsh for the fragile chemistry of biology. Ross 128, approximately 11 light-years. A quiet red dwarf with one confirmed planet. Ross 128b, a world roughly 1.35 times the mass of Earth. Temperatures there are estimated to allow liquid water on the surface under certain conditions. Whether it has an atmosphere, whether anything is there to hold warmth and shield any chemistry that might be trying to happen, remains unknown. We detect its presence as a slight wobble in the movement of its star, a gravitational signature, a mathematical ghost. Nothing more yet. The Teegarden star system, roughly 12.5 light-years away, sitting in the constellation Aries. One of its worlds, Teegarden's star B, scored near the top of the Earth Similarity Index when it was confirmed in 2019, a ranking that attempts to quantify how closely an exoplanet's basic parameters resemble those of Earth. Surface temperatures are estimated near 20 degrees Celsius under optimistic assumptions about its atmosphere. A temperature at which liquid water pools easily, at which chemical reactions proceed briskly, at which life, on the one world we know it has appeared, flourishes in extraordinary variety. A radio signal sent toward Teegarden's star B in the year 2026 would arrive in 2038. Any reply, assuming something there received it and answered immediately, would not reach Earth until 2050. A conversation. One exchange of messages. 24 years. And these are the nearby stars, the local neighborhood, the galactic equivalent of the houses visible from your front porch on a clear night. The TRAPPIST-1 system commanded global attention in February of 2017, when a team of astronomers using the European Southern Observatory's TRAPPIST telescope and several other instruments announced the discovery of 7 roughly Earth-sized planets orbiting a single dim red dwarf star. Not one, not two. 7 worlds, arranged in compact orbits around a star, small enough and cool enough that its habitable zone, the band of distance where liquid water could exist, began at roughly 1/10 of the distance between Earth and our Sun. At least 3 of those 7 worlds sit within or near that habitable zone. 7 worlds, 1 star. The most densely packed system of potentially temperate planets ever found. And TRAPPIST-1 sits approximately 40 light-years from Earth. A signal sent toward TRAPPIST-1 the year the Second World War ended, in 1945, would be arriving there approximately now, in 2025. Any civilization in that system receiving it tonight would be sending a reply that would not reach us until 2065. Most people alive today would not live to receive that reply. 40 light-years. And in the language of the galaxy, 40 light-years is nothing, an almost embarrassing distance, a footstep on a road that stretches halfway across the continent. The Milky Way spans at least 100,000 light-years across its visible disk. Some measurements, accounting for the sparse outer stellar halo that fades gradually into intergalactic space, suggest the galaxy may extend to 200,000 light-years or more in its full diameter. The center of our own galaxy, the churning, radiating core where stars pack so tightly They are separated by distances measured not in light years, but in light months, where the supermassive black hole Sagittarius A star sits in patient ancient darkness, absorbing whatever drifts too close, lies approximately 26,000 light years from Earth. Light that left the galactic center when early anatomically modern humans were painting aurochs and handprints on the walls of caves in what is now France and Spain has still not reached us. It is traveling toward us now, has been traveling toward us for 26,000 years, and will arrive in roughly 24,000 more. When that light finally crosses our threshold, if anyone is still here to receive it, it will be carrying an image of the galactic core as it appeared, before agriculture existed, before writing existed, before any human being had sailed a boat or smelted metal or asked a recorded question about the nature of the stars. These are not decorative facts. They are the architecture of the problem. The Milky Way contains an estimated 200 to 400 billion stars. Statistical analysis of data from the Kepler Space Telescope, a planet-hunting observatory that stared at a patch of sky roughly the size of your fist, held at arm's length, and detected the tiny dimming of starlight as planets crossed their host stars, suggests that something like 20% of Sun-like stars host an Earth-sized planet in their habitable zone. Applied across even a conservative estimate of the galaxy's stellar population, this yields approximately 40 billion potentially habitable worlds around Sun-like stars alone. Add red dwarf stars, which are far more numerous. They outnumber Sun-like stars by roughly 5 to 1 in our galactic neighborhood, and which also host rocky planets in temperate orbits, and the number of potentially habitable worlds climbs considerably higher. Some estimates place it in the hundreds of billions of worlds where the basic conditions for life as we know it might be met. Hundreds of billions of surfaces where water might pool, where organic molecules might assemble into chains of increasing complexity, where chemistry might inch, over millions or billions of patient years, toward the extraordinary accident that is biology, scattered across a disk 100,000 light-years wide. Now let us watch what happens when a spacecraft actually tries to cross these distances. Let us climb the speed ladder, slowly and honestly, and see what we find at each rung. At 1% of the speed of light, a spacecraft would travel at approximately 3,000 kilometers per second. In more familiar terms, roughly 10.8 million kilometers per hour. This is roughly 176 times faster than Voyager 1. No human-built object has ever come close to this speed. The Parker Solar Probe, the fastest spacecraft ever flown relative to the Sun, achieved its peak velocity of roughly 190 kilometers per second during its closest solar passes, close enough to the Sun that the star's gravity accelerated it to records no rocket had previously achieved. 1% of light speed is nearly 16 times faster than that record. A journey to Proxima Centauri at 1% of light speed, approximately 425 years. Columbus crossed the Atlantic in 1492. A ship launched that same year toward Proxima Centauri, traveling at 1% of the speed of light without slowing, without stopping, maintaining that extraordinary velocity every second of every day, would still not have arrived. The crew would have been dead for centuries. Their grandchildren would have been dead for centuries. Their great-great-great-great-great-grandchildren would still be generations away from landfall. The European countries that commissioned the voyage in this thought experiment might not exist in any recognizable form. The languages spoken aboard the ship at launch might be mutually unintelligible to anyone still living. 1% of light speed. 425 years. For the nearest star. For Teagardens star B, one of the most Earth-like worlds known, at 12.5 light-years. The journey at 1% of light speed takes 1,250 years. For TRAPPIST-1, at 40 light-years, it takes 4,000 years. That is older than the Egyptian pyramids. A spacecraft launched toward TRAPPIST-1 at 1% of the speed of light at the dawn of ancient Egypt would still be in transit today, with another 2,000 years of travel remaining. So we go faster. 5% of light speed, roughly 15,000 kilometers per second. At 5%, the journey to Proxima Centauri compresses to approximately 85 years. An astronaut departing at age 20 might arrive at age 105. Biologically possible at the outermost edge of human longevity, under conditions that have never existed and would be extraordinarily difficult to engineer. The human body is not designed for decades in microgravity, in confined spaces, in constant low-level radiation. But at least the timescale overlaps with a single human life, however barely. To Teagardens star at 5% of light speed, 250 years, 2.5 human lifetimes. To TRAPPIST-1, 800 years. Any candidate world more than about 10 light-years away still requires a multi-generational commitment at this speed. 10% of light speed. 30,000 kilometers per second. Roughly 108 million kilometers per hour. Fast enough that if you fired a beam at the moon, the return signal would come back in under a third of a second. Fast enough to cross the entire diameter of Earth in less than a millisecond. At 10% of light speed, the journey to Proxima Centauri takes roughly 42 years. A mission launched when a crew member is 25 arrives when they are 67. Conceivable. Brutal in every physiological and psychological dimension. And requiring a propulsion capability approximately 1,600 times beyond anything humanity has ever built or seriously prototyped. At 10% of light speed, the journey to Teagardens star B takes 125 years. 2 full human lifetimes. The journey to TRAPPIST-1 takes 400 years. Any star beyond approximately 15 light-years requires multi-generational timescales, even at this extreme velocity. In 2016, the Breakthrough Starshot project was announced with $100 million in initial funding from Russian-Israeli billionaire and physicist Yuri Milner, with public support from Stephen Hawking and others. The vision was specific and ambitious. Accelerate a spacecraft to 20% of the speed of light, allowing it to reach Proxima Centauri in roughly 21 years. A scientist in their early 30s who helped design the mission might live to receive data back. The spacecraft they proposed was not a vessel in any traditional sense. It was not a probe with instruments and a power supply and a camera on a tripod. It was a gram-scale chip. A wafer of silicon and circuitry weighing approximately 1 gram, roughly the mass of a paperclip, attached to a reflective sail perhaps 4 meters across. The chip would carry a tiny camera, minimal computing hardware, and a laser transmitter for sending data back. The entire spacecraft, chip and sail together, would weigh roughly a gram. The energy source was not aboard the spacecraft. It was on the ground. A phased array of lasers with a combined output of 100 gigawatts. 100 gigawatts, approximately the entire electrical generating capacity of Japan. This colossal beam of light would be focused through precision optics onto the sail for roughly 10 minutes, during which radiation pressure, the gentle push of photons bouncing off a reflective surface, would accelerate the Gram scale chip to 20% of light speed. By September 2025, Scientific American reported that Breakthrough Starshot had been placed on indefinite hold. Of the $100 million pledged, approximately $4.5 million had actually been spent. The engineering challenges were simply too severe. The laser array required gigawatt-scale infrastructure that no existing facility could provide. The sail material needed to be almost perfectly reflective, because absorbing even a tiny fraction of 100 gigawatts would vaporize it in milliseconds. The chip needed to survive acceleration forces of thousands of g during the 10-minute burn, then endure decades of interstellar space, arriving at Proxima Centauri still functional enough to take pictures and transmit them home across 4 light-years, using a laser the size of your fingernail. And this was for a flyby, not a mission in any meaningful sense. A gram of silicon screaming through the Alpha Centauri system at 60,000 kilometers per second, getting a few hours of observation time before vanishing into interstellar space forever, unable to slow down, unable to orbit, unable to land, unable to return. This is the state of the most ambitious, best-funded attempt in human history to send even the tiniest, most minimal conceivable object to the nearest star. Somewhere in the quiet of tonight, in the dark behind your closed eyes, let that settle. The numbers do not get more forgiving from here. Let the room hold you. The ceiling above, the floor below, the silence on all sides. There are many hours still ahead, and we are going to spend them moving slowly, honestly, through the full picture of what these distances mean. Because the travel time problem is only the first wall, the second is energy, and it is higher. Part 3. The Energy Wall. Every spacecraft humanity has ever launched has been powered by the same fundamental mechanism. Controlled explosions, liquid hydrogen and liquid oxygen, held in separate tanks at cryogenic temperatures, pumped together into a combustion chamber where they combine with extraordinary violence. The reaction produces superheated steam, water in its most energetic form, which blasts out of a nozzle at roughly 4.5 kilometers per second. The rocket moves forward. Newton's third law, as simple and as old as falling apples, doing exactly what it always does. This technology carried human beings to the surface of the moon. It placed the Hubble Space Telescope in orbit around Earth. It launched the Mars rovers, the Voyager probes, the Cassini spacecraft that spent 13 years orbiting Saturn and discovered geysers of water vapor erupting from the south pole of its moon Enceladus. Chemical propulsion is one of the most thoroughly tested and refined engineering achievements in all of human history. It works. It works beautifully in the domain for which it was built. For interstellar travel, it is laughably, categorically, and in no way fixably inadequate. The reason comes down to a single equation that has governed all of rocketry since 1897, when a Russian schoolteacher and self-taught mathematician named Konstantin Tsiolkovsky derived it at his kitchen table in the small city of Borovsk. Tsiolkovsky spent much of his adult life thinking about space travel at a time when the very idea was considered the territory of fiction and fantasy. He lived in poverty. He was largely deaf from childhood scarlet fever. He taught arithmetic and geometry at a local school and spent his evenings doing calculations. And the equation he derived, now known as the Tsiolkovsky rocket equation, is the single most important equation in spacecraft design. Everything that has ever left Earth is a consequence of it. The equation says this: the final velocity of a rocket depends on the exhaust velocity of its engine multiplied by the natural logarithm of the ratio between its initial mass and its final mass. What this means in practice is that the fuel requirements grow exponentially with the desired final speed. Not linearly, not gently, exponentially. Every time you want to go significantly faster, the fuel required does not merely increase. It balloons, then doubles the balloon, then doubles that. Chemical rockets eject exhaust at roughly 4 to 5 kilometers per second. To reach 10% of the speed of light, 30,000 kilometers per second, using chemical propulsion, the mass ratio required is a number so astronomically large it is effectively meaningless. You would need more fuel than exists in the observable universe to accelerate a single kilogram to 1% of light speed using the energy stored in chemical bonds. This is not an approximation. It is simple arithmetic applied to a known exhaust velocity. The rocket equation does not negotiate. Every serious proposal for interstellar propulsion therefore abandons chemical energy entirely and looks to nuclear physics. Nuclear reactions release approximately 1 million times more energy per kilogram of fuel than chemical reactions. 1 kilogram of uranium undergoing fission produces roughly 80 trillion joules. 1 kilogram of the best chemical propellant produces about 13 million joules. The difference is a factor of 6 million, and that factor matters enormously when you are trying to reach the stars. Nuclear thermal propulsion, the technology studied most extensively during the American NERVA program in the 1960s, uses a nuclear reactor to heat a propellant, typically hydrogen, to extreme temperatures before expelling it through a nozzle. The exhaust velocity is roughly double that of chemical rockets. Still far short of what interstellar travel requires, but a meaningful improvement. The NERVA program produced functioning nuclear rocket engines. They were tested. They worked. They were canceled in 1973, partly for budgetary reasons and partly because they were designed for missions, a crewed Mars expedition, that were also canceled. Nuclear pulse propulsion goes further. The concept, studied seriously in the late 1950s under the classified Project Orion and later revived in various forms, involves detonating small nuclear devices behind a spacecraft at regular intervals, using the shock wave from each explosion to push a large pusher plate attached to the vehicle. The energy available from nuclear explosives is far greater than any continuous thrust system, and the theoretical performance of a well-designed pulse propulsion spacecraft could reach velocities of perhaps 1 to 5% of light speed with reasonable mass ratios. Not fast enough, but closer, and requiring that you essentially travel aboard a series of controlled nuclear explosions, which raises questions of its own. Nuclear fusion, the process that powers the sun, combining light nuclei into heavier ones and releasing energy in the process, offers still higher performance. A fusion rocket could achieve exhaust velocities in the range of 10,000 to 30,000 kilometers per second, somewhere between 3 and 10% of the speed of light. At these exhaust velocities, the mass ratios required to reach 10% of light speed become challenging, but not physically absurd. A ship might need to be 10 to 20 times heavier at launch than at arrival, rather than 100 or 1,000 times heavier. The problem is that no fusion rocket exists. No fusion engine of any kind exists. The entire field of fusion energy research, despite 7 decades of sustained effort and investment in the tens of billions of dollars across multiple countries, has not yet produced a power plant that generates more energy than it consumes. The ITER experimental reactor in southern France, the most ambitious fusion project ever attempted, an international collaboration involving 35 nations and costing more than 20 billion euros, is designed to demonstrate net energy gain from fusion for the first time. It will not achieve its primary fusion experiments until the early 2030s at the earliest, after decades of delays and repeated budget overruns. And it is a stationary facility the size of a large building. It generates no thrust. It has no nozzle. Converting the physics of ITER into a compact, flight-ready engine capable of operating continuously for years or decades in deep space represents an additional engineering leap whose magnitude is difficult to overstate. Antimatter propulsion represents the theoretical maximum of energy density available within known physics. When a particle of matter meets its antiparticle, a proton meets an antiproton, an electron meets a positron. Both particles annihilate completely, converting 100% of their combined mass into pure energy. No waste, no exhaust, no byproducts except gamma radiation and secondary particles, which can in principle be directed to generate thrust. The conversion efficiency is perfect in a way no other energy source approaches. Fission converts roughly 0.1% of mass into energy. Fusion, roughly 0.7%. Chemical reactions, roughly 0.0000001%. Antimatter converts 100%. The energy density is staggering. A single gram of antimatter annihilating with a gram of normal matter releases approximately 180 terajoules, roughly equivalent to the Hiroshima bomb. A kilogram of antimatter annihilating with a kilogram of matter releases about 180,000 terajoules. For context, burning a kilogram of rocket fuel releases about 13 megajoules, roughly 13 million joules. Annihilating a kilogram of antimatter with matter releases 1.8 times 10 to the 17th power joules. The ratio is approximately 14 billion to 1. The problem is production. The total amount of antimatter ever created by all of humanity's particle accelerators combined, every CERN run, every Fermilab collision, every experiment ever conducted, is estimated at roughly 20 nanograms, 20 billionths of a gram. It was produced at extraordinary expense, required vast infrastructure, and nearly all of it annihilated almost instantly on contact with the walls of whatever container it was briefly held in. Producing even 1 gram of antimatter using current technology would cost on the order of tens of trillions of dollars and require continuous accelerator operation for a time exceeding recorded human history. But there is a deeper problem with antimatter that receives far less attention than it deserves, and it fundamentally changes the nature of what antimatter propulsion could ever mean. Antimatter is not a source of energy. It is a storage medium. Creating an antiparticle requires investing at least as much energy as that antiparticle will release upon annihilation. The law of conservation of energy is absolute and non-negotiable. You cannot get more energy out of antimatter than you put into making it. At perfect theoretical efficiency, an efficiency no real process approaches, you get exactly the same energy back. In every real scenario, you get significantly less, because converting energy from one form to another always involves losses. What this means is that a civilization fueling an interstellar mission with antimatter must first generate all of the required energy through some other means. Fusion, solar collectors, nuclear fission, whatever power source they possess. Then they must convert that energy into antimatter, paying an enormous efficiency penalty. Then they must store the antimatter in perfect isolation from normal matter, in magnetic or electric containment fields, in a vacuum so pure that not a single stray molecule can drift into contact. For the months or years of mission preparation, and then for the decades of the journey itself. Current laboratory traps can hold small numbers of anti-hydrogen atoms for minutes or hours. Scaling this to hold grams or kilograms of antimatter for decades, with no failure of the containment system, represents a technological challenge that does not currently have even a theoretical solution. Antimatter does not solve the energy problem of interstellar travel. It relocates it, and in doing so, wraps it in additional layers of inefficiency and engineering complexity that make the total energy budget even more punishing than the raw calculations suggest. Laser sail propulsion, the approach chosen by Breakthrough Starshot, sidesteps the rocket equation entirely by leaving the energy source behind. The spacecraft carries no propellant at all. A ground-based or space-based laser array accelerates it via radiation pressure, the gentle but accumulating push of photons bouncing off a reflective surface. Because the spacecraft carries no fuel, the tyranny of the exponentially escalating mass ratio is removed. The laser array can draw power from conventional sources, can be scaled up incrementally, and can in principle be reused for multiple launches. This is why laser sails represent the most plausible pathway to relativistic speeds for small payloads. The physics is sound. The energy comes from a fixed installation. The spacecraft can be minimal. But a laser sail can only be pushed. It cannot be stopped. A spacecraft accelerated to 20% of light speed by a laser array arrives at Proxima Centauri, traveling at 60,000 kilometers per second. It passes through the entire star system in a matter of hours, perhaps 4 or 5 hours of useful observation time as it approaches, passes, and recedes. It cannot decelerate. It has no engine, no propellant, no brakes of any kind. It cannot enter orbit. It cannot conduct sustained scientific observations. It cannot deploy instruments. It cannot land. It cannot return. It screams through the most compelling nearby stellar neighborhood in the sky at a sixth of the speed of light, snaps a handful of images with its paperclip mass camera, and then continues into interstellar darkness forever. That is not a mission. That is a photograph taken from a speeding car. Which brings us to the wall that receives far less attention than it deserves. The one that doubles every number we have discussed, and more. Deceleration. Every discussion of interstellar travel focuses on acceleration. How fast can we get going? What engine can produce enough thrust? What exhaust velocity do we need? The glamour is in the going. But physics is indifferent to direction. Arriving at a destination, actually stopping, entering orbit, conducting the kind of sustained observations that could tell us whether a world has life on it, requires slowing down. And slowing down costs exactly as much energy as speeding up. A spacecraft that accelerates to 10% of the speed of light and then needs to decelerate to rest at the destination must spend the same amount of energy twice, applied in opposite directions. Twice the energy budget, minimum. But it is worse than twice, because the fuel needed for deceleration must itself be accelerated during the first half of the trip. If you need to carry 50 tons of deceleration fuel, you must also accelerate those 50 tons to cruise speed during the outbound leg. That requires more fuel. More fuel means more mass. More mass means more fuel to accelerate that mass. For a conventional rocket, the deceleration requirement does not double the mission's mass ratio. It squares it. A ship requiring a mass ratio of 20 to 1 for acceleration alone needs approximately 400 to 1 for full acceleration plus deceleration. For every single kilogram of payload you want to deliver to the destination at rest, you need 400 kilograms of fuel at departure. This is not a minor engineering complication. It is the difference between difficult and impossible. The Project Daedalus design study, conducted by the British Interplanetary Society through the 1970s and completed in 1978, was the most thorough serious engineering study of an interstellar probe ever undertaken. The team spent 5 years designing a fusion-powered craft capable of reaching Barnard's star, 5.96 light-years away, in roughly 50 years of flight. The design called for a 2-stage vehicle weighing approximately 54,000 metric tons at launch, with the first stage using inertial confinement fusion to accelerate the second stage to roughly 12% of the speed of light. The Daedalus design made no provision for deceleration. It was a flyby mission by deliberate necessity. Not because deceleration was forgotten, but because when the team ran the numbers, accounting for deceleration made the required mass ratio physically impossible to build. Even as a purely theoretical exercise, unconstrained by budget or materials, the deceleration problem was too severe to incorporate. A follow-up study called Project Icarus attempted to address it. The mass requirements roughly quadrupled, and the mission design became increasingly speculative. Some researchers have proposed alternative deceleration mechanisms that avoid carrying onboard fuel. A magnetic sail could theoretically interact with the charged particles of the interstellar medium, creating drag that gradually slows the spacecraft. At 10% of light speed, the incoming hydrogen atoms carry enough momentum to exert a braking force on a sufficiently large magnetic field. But the interstellar medium is extraordinarily sparse, roughly 1 atom per cubic centimeter, and the braking force is tiny. Decelerating from 10% of light speed using a magnetic sail would take decades and would begin long before the destination, requiring the spacecraft to deploy its sail millions of kilometers in advance and spend much of its journey crawling gradually slower. Another concept uses the destination star's own radiation pressure as a brake. A large reflective sail deployed near the target star would be pushed backward by the star's photons, opposing the spacecraft's motion. Elegant in principle. But at 10% of light speed, the kinetic energy of the spacecraft is so enormous that stellar radiation pressure would need an impractically long time to bleed it off. The spacecraft would likely overshoot the system entirely before slowing sufficiently. The deceleration problem is not a detail to be solved later. It is the core of the energy wall. Any civilization in this galaxy, any civilization at all, regardless of age or sophistication, that wants to send a spacecraft to another star and have that spacecraft actually arrive, slow down, stay, and look around, must account for deceleration. And when they do, the energy and mass requirements roughly square themselves, converting an already staggering challenge into something that borders on the physically unachievable for any payload larger than trivial. There is one final concept in the physics of interstellar travel that is often presented as a solution, and which deserves honest examination before we move on. It is called time dilation. It is real. It has been experimentally confirmed, and it is, in the end, not the escape it first appears to be. Einstein's special theory of relativity predicts that time passes more slowly for objects moving at high velocities relative to a stationary observer. This is not an illusion or a perceptual quirk. It is a genuine feature of spacetime. An atomic clock flown aboard a fast-moving aircraft accumulates slightly less elapsed time than an identical clock left on the ground. GPS satellites, which move quickly relative to Earth's surface, require relativistic corrections to remain accurate, corrections that have been measured and confirmed to extraordinary precision. Time dilation is as real as gravity. At low speeds, the effect is negligibly small. At 10% of the speed of light, time passes roughly 0.5% slower for the traveler than for a stationary observer. A journey that takes 42 years by Earth's clocks would be experienced as about 41 years and 9 months by the crew. Not a meaningful difference. But at very high fractions of the speed of light, the effect becomes dramatic. At 90% of light speed, time passes roughly 2.3 times slower for the traveler. At 99%, roughly 7 times slower. At 99.9%, roughly 22 times slower. In principle, a crew traveling at 99.9% of the speed of light could cross the galaxy's 100,000 light-year diameter in approximately 4,500 years of subjective experience, while 100,000 years pass on Earth. This sounds like a solution. It is not. Consider what it actually means. To take advantage of time dilation in any meaningful way, you must first reach those extreme velocities. The energy required to accelerate a spacecraft to 99% of the speed of light is not merely large. It is staggering beyond almost any useful frame of reference. The relativistic kinetic energy of a 100,000 kilogram vessel traveling at 99% of light speed is approximately 6 times the rest mass energy of the ship, roughly 5.4 times 10 to the 22nd power joules. That is approximately 100 times the total annual energy consumption of human civilization, concentrated into a single propulsion event. And then there is the deceleration problem, doubling everything. And then there is the homeworld problem. Time dilation solves the traveler's subjective experience of the journey. It does nothing for the civilization that launched the mission. If a crew departs at 99% of the speed of light toward a star 100 light years away, the journey takes slightly more than 100 years of Earth time, but only about 14 years of crew time. The crew returns, biologically 14 years older, to a world that has aged by more than 2 centuries. Everyone they knew is dead. The society that built their ship has been transformed beyond recognition. The specific knowledge they were carrying back, their data, their observations, their samples, would be received by people living 2 centuries after the mission was launched. Whether those people can still make sense of the data, whether the scientific infrastructure to analyze it still exists in recognizable form, is an open question. Time dilation turns interstellar travelers into time travelers in only one direction. It does not solve the loneliness of the crossing. It merely relocates it. The traveler is isolated from their own time as thoroughly as from their own space. Breathe. Let the weight of the pillow hold your head. We have established the distances. We have established the energy. We have looked at the deceleration trap and the time dilation illusion. Now we need to talk about what happens during the journey itself, what the interstellar environment does to everything that tries to cross it. Because the dark between stars is not a passive emptiness waiting patiently for travelers to pass through. It is an adversary, patient, indifferent, and thorough. Part 4. The Hostile Dark. There is a comfortable image that the phrase interstellar space tends to produce. Emptiness, silence, a vast and frictionless nothing through which a spacecraft might glide indefinitely, unimpeded, untouched, the way a stone skips across still water before the water eventually claims it. The void of popular imagination is peaceful. It is the background of science fiction, the ink-black canvas against which the drama of exploration plays out. It does nothing. It waits. This image is wrong. The space between stars is not empty. It is filled with what astronomers call the interstellar medium, a thin, cold, ancient haze of hydrogen atoms, helium, trace amounts of heavier elements, and microscopic solid particles. The hydrogen exists partly as neutral atoms, partly as ions stripped of their electrons by the ultraviolet radiation from distant stars, and partly as molecules in cold, dense clouds where it can form pairs. The dust particles are submicroscopic grains of silicate minerals, carbon compounds, and ices, remnants of stellar winds and supernova ejecta that have drifted through space for billions of years, slowly accreting mass, slowly changing composition, waiting. The average density of the interstellar medium is approximately 1 atom per cubic centimeter. In any laboratory on Earth, this would qualify as a vacuum far more extreme than anything achievable with the best pump. Compared to the air in the room where you are lying now, which contains roughly 2.5 times 10 to the 19th power molecules per cubic centimeter, roughly 25 billion molecules in every centimeter of the air above your face. The interstellar medium is essentially nothing. But at relativistic speeds, sparseness is completely irrelevant. What matters is not density. What matters is kinetic energy. And kinetic energy scales with the square of velocity. A spacecraft traveling at 10% of the speed of light, 30,000 kilometers per second, does not drift through the interstellar medium. It collides with it at 30,000 kilometers per second. Every hydrogen atom drifting peacefully in its path impacts the spacecraft's forward surface with the energy of a high-speed particle in a particle accelerator. The hydrogen atoms are effectively stationary. It is the spacecraft that is moving. But from the perspective of the spacecraft's hull, they arrive like radiation, a constant, relentless bombardment from the front. The cumulative effect, integrated across years of transit, is equivalent to sustained irradiation from a particle beam of considerable intensity. Electronic components degrade. Semiconductor junctions accumulate damage. The atomic structure of metals develops defects. Shielding slowly ablates as it absorbs the impacts and converts the kinetic energy of incoming particles into heat that must be radiated away. Dust grains present a more immediate and dramatic hazard. The interstellar medium contains solid particles, silicate grains, carbon compounds, crystalline ice, typically ranging from a fraction of a micrometer to perhaps a few micrometers in their largest dimension. Hold a human hair between your fingers. A typical interstellar dust grain is perhaps 1/100th the width of that hair. Invisible, weightless in any practical sense. You would breathe millions of them without noticing, but kinetic energy cares nothing for size. A dust grain massing 1 nanogram, 1/1000th of a gram, striking a spacecraft at 10% of light speed carries a kinetic energy of approximately 450 joules. That is comparable to the muzzle energy of a fired handgun round, a single, invisible, weightless speck of interstellar dust, and it hits with the kinetic energy of a bullet. At 20% of light speed, the energy quadruples. Each grain becomes, effectively, a rifle round. Over a 42-year journey to Proxima Centauri, a spacecraft would encounter millions, perhaps billions, of such particles. The cumulative effect on any unshielded structure would be catastrophic. Forward-facing hull material would erode. Optical instruments pointed ahead would be sandblasted into opacity. Thermal regulation systems involving external surfaces would be compromised. The spacecraft would arrive, if it arrived, abraded, pitted, its leading surfaces transformed by decades of ballistic impact. Shielding can address this in principle. A thick enough layer of ablative material at the spacecraft's leading face would absorb and disperse the impacts, sacrificing itself gradually so that the instruments behind it survive. This is conceptually similar to the heat shields used during atmospheric entry on Earth, which ablate deliberately to carry away heat. The principle is sound, but every kilogram of shielding added to the craft increases total launch mass. More mass means more fuel to reach the target speed. More fuel means more mass to accelerate. The rocket equation's compounding penalty applies to every addition, and shielding capable of protecting a meaningful spacecraft across 40 years of relativistic dust bombardment would need to be substantial. Cosmic rays add another layer of degradation. These are high-energy particles, primarily protons, but also heavier nuclei stripped bare of their electrons, accelerated to near-light speeds by the shock waves of supernova explosions, by the violent jets of active galactic nuclei, by the magnetic fields of neutron stars and other extreme astrophysical objects. They permeate the galaxy in all directions at all times. On Earth, we are shielded from most of them by two mechanisms: our atmosphere, which has enough mass above any point on the surface to absorb and scatter cosmic rays before they reach the ground, and Earth's magnetic field, which deflects the lower energy particles, channeling them toward the poles where they produce auroras. In interstellar space, there is no atmosphere. There is no magnetic field. There is nothing between the spacecraft and the full isotropic flux of galactic cosmic radiation. Cosmic rays penetrate deeply. They ionize atoms inside electronic circuits, dislodging electrons from their orbits and creating electrical charges in places where none were intended. These spurious charges flip bits in computer memory, changing a stored 0 to a 1 or vice versa, at a rate that depends on the flux of radiation and the sensitivity of the hardware. A single cosmic ray particle passing through a modern microprocessor can corrupt dozens of memory bits simultaneously in what is called a single-event upset. On Earth, radiation-hardened electronics are designed to tolerate modest rates of such upsets. In deep interstellar space, the rates would be far higher, and over a journey lasting decades, the accumulated damage to any electronic system would require either extraordinary redundancy, continuous error correction of a thoroughness not yet demonstrated in hardware, or regular physical replacement of components, an option not available to an autonomous probe. For biological systems, cosmic rays are a direct physical threat. High-energy particles passing through tissue break chemical bonds in DNA. Some of these breaks are repaired correctly by cellular machinery. Some are repaired incorrectly, producing mutations. Some are not repaired at all, triggering cell death. Over time, the accumulated damage raises the probability of cancer, impairs the function of rapidly dividing cells, immune cells, intestinal lining cells, blood-forming cells, and may affect the nervous system in ways that only became apparent decades after exposure. NASA has studied the effects of cosmic radiation extensively in the context of Mars missions, which would expose astronauts to elevated radiation for roughly 2 to 3 years of transit. The findings are consistently sobering. Lifetime cancer risk increases significantly. Studies in rodents exposed to simulated galactic cosmic ray environments showed measurable changes in brain structure, including inflammation in hippocampal tissue associated with memory formation and impaired performance on cognitive tasks. A journey to Proxima Centauri at 10% of light speed takes 42 years. The cumulative radiation dose across 42 years in interstellar space, far from any protective field, bathed continuously in the full, unshielded flux of galactic cosmic radiation, plus whatever additional dose comes from the interstellar medium's particle collisions, would be orders of magnitude higher than a Mars mission. No current or near-future medical intervention could address the cumulative biological damage. And beyond radiation, beyond dust, beyond the slow particle bombardment, there is simply time. Machines fail, not dramatically, not in a single, catastrophic moment, but persistently, in the slow and irreversible accumulation of small degradations. Seals develop microscopic fractures. Metal fatigues under the cycling stress of temperature variations during course corrections. Bearings wear imperceptibly. Electronic components drift out of specification. A transistor that was perfectly calibrated at launch performs slightly differently after a decade, slightly more differently after 2, unpredictably after 3. Lubricants, if any moving mechanical parts require them, evaporate gradually into the vacuum that surrounds them. Software running continuously accumulates subtle errors in memory, tiny corruptions that propagate slowly through calculations until some downstream system begins behaving in ways no engineer anticipated. The International Space Station, the most complex structure ever assembled in space, built by the combined engineering resources of 15 nations, has required continuous resupply flights from Earth and constant hands-on maintenance by its rotating crews. It has been operational for roughly 25 years. It already shows significant wear in multiple systems. And it orbits in a relatively benign environment, only a few hundred kilometers above Earth's protective atmosphere and magnetic field, with resupply available every few months. An interstellar spacecraft would need to operate for decades, without resupply from any source, without replacement parts from any manufacturer, without the possibility of rescue if something failed. Every component aboard would need either to last the full mission duration without service, or to be repairable from spare parts carried aboard, or to be manufactured from raw materials using onboard fabrication systems of a capability and reliability we have not yet built. Every possible failure mode would need to be anticipated before launch, because there would be no one reachable in time to help. The closest help would be light hours, or light years away. The Voyager probes have survived nearly 50 years of spaceflight. Both are experiencing progressive failures, power output from their radioisotope thermoelectric generators declining, some instruments no longer functional, communication systems requiring increasing ingenuity from engineers on Earth to maintain. They are impressive machines, but they are also simple by modern standards, and they are failing at 47 years. Extending operational lifetimes measured in decades to operational lifetimes measured in centuries or millennia, while simultaneously operating under the additional stresses of relativistic dust bombardment and full cosmic ray flux, represents an engineering challenge without precedent. We have not yet mentioned biological lifespan. A crewed vessel traveling to Proxima Centauri at 10% of light speed takes 42 years. A mission to a star 20 light-years away at the same speed takes 200 years. No human alive today, and no human who will be born under biology as currently understood, can live 200 years. The average healthy lifespan in developed nations is roughly 75 to 80 years. Even the most optimistic projections for life extension research, the scenario where anti-aging medicine delivers decades of additional healthy years over the coming century, would need to achieve a factor of 2 or 3 improvement to make even the nearest multi-generational star systems accessible within a single life. Generation ships have been proposed as the answer. Vessels large enough and self-contained enough to sustain a self-reproducing human population across many generations, so that the people who arrive at the destination are the great-great-grandchildren of the people who departed. The engineering challenges are staggering in their scope. Such a vessel would need to be a fully closed ecological system, recycling every molecule of air, water, and nutrient indefinitely, with no external inputs for centuries. It would need to support a population large enough to maintain genetic diversity across many generations without the accumulation of harmful inbreeding. Geneticists generally estimate a minimum of several hundred to several thousand individuals for a multi-generational voyage. It would need power sources operating without resupply for millennia. It would need medical facilities capable of addressing every condition that might arise, with no possibility of outside consultation. But the deeper challenge is social, and it is the one that rarely gets the attention it deserves. No human institution has maintained a coherent purpose across more than a few centuries. Some religious institutions have preserved core beliefs for 1,000 years or more, but even they have undergone radical transformations in doctrine, practice, governance, and identity over that span. The Catholic Church of the 13th century and the Catholic Church of the 21st century share a name and a lineage, but differ profoundly in nearly every other dimension. Nation-states dissolve, merge, fragment. Languages drift so far from their origins that 2 centuries of separation renders them mutually unintelligible. Modern English is essentially unrecognizable as the same language spoken in England 1,000 years ago. The idea that a ship-based society could preserve not merely its social cohesion, but its mission objectives, the specific technical knowledge of where they are going and why they are going there, the institutional motivation to complete a journey that no living person chose, across 30 or 50 generations, is a social engineering challenge with no historical precedent. Every generation born on that ship would be a generation that never agreed to the voyage, never had the option of a different life, and would arrive at the destination, if they arrived at all, as people whose entire experience of existence had been the interior of a vessel, crossing an emptiness they had read about in historical records, but never seen with their own eyes. Suspended animation offers a theoretical alternative. The idea of placing crew members in a state of metabolic suspension so profound that biological aging effectively halts for the duration of the journey. Science fiction has explored this concept extensively, typically as cryogenic freezing in which passengers are cooled near absolute zero and later revived unchanged. The appeal is obvious. A crew placed in perfect suspension at departure would emerge at arrival biologically unchanged, having subjectively experienced nothing of the intervening decades. The practical obstacles are severe. Water expands when it freezes, and the ice crystals that form as tissue cools rupture cell membranes. Vitrification, a technique of ultra-rapid cooling that produces an amorphous glass rather than crystalline ice, has been successfully demonstrated in small tissue samples and isolated organs. Whole organ vitrification, followed by revival, has been achieved in a small number of experimental cases. Whole body suspension and revival of a complex multicellular organism with an intact nervous system remains far outside current capability, and the obstacles are not merely engineering problems. They involve fundamental aspects of how cells respond to extreme cold and how damage propagates through interconnected biological systems in ways that repair mechanisms cannot easily address. And even if perfect suspended animation were achievable, it would not solve the radiation problem. A crew member in complete metabolic suspension is still a collection of biological molecules. Cosmic rays still pass through them. DNA breaks still accumulate across the decades of the crossing, in a body too dormant to repair any of it. The traveler who woke at the destination might be biologically preserved in one sense and quietly compromised in another, carrying in their cells the invisible record of a journey their conscious mind never experienced. There is one more dimension of the problem worth considering before we move on, because it illuminates something about interstellar travel as a civilizational undertaking rather than a purely engineering one. Suppose a civilization launches a generation ship toward a star 500 light-years away. At 5% of the speed of light, the journey takes 10,000 years. The ship departs with its settlers and its mission parameters locked in at launch. Meanwhile, the home civilization continues. Technology advances. Decades pass, and what seemed like the pinnacle of engineering at departure begins to look like a first draft. A century later, a faster ship can be built. 2 centuries later, a far faster one. It is entirely possible, and given any reasonable trajectory of technological development, likely, that a mission launched several centuries after the original would overtake it and arrive first. The descendants of the original settlers, 30 generations removed from anyone who made the original decision, would arrive at a destination already colonized by their own civilization's later and faster efforts. This is sometimes called the incessant obsolescence problem. It creates a powerful rational argument against launching any interstellar mission before propulsion technology is fully mature. But there is always a reason to wait for better technology. The mission never launches. The infinite regress of anticipated improvement combines with the staggering cost, duration, and risk of any realistic mission to produce a civilizational inertia against departure that may be essentially insurmountable. And yet the ship continues, through the particle bombardment, through the component failures, through the decades of recycled air and the same corridors and the same faces and the faint stars in the viewports that barely seem to move across a human lifetime, through the quiet erosion of purpose that long isolation demands of anything biological. This is the interior of the hostile dark, not just the environment outside the hull, the environment inside it. We are far from home now, and we are approaching the part of the journey where the silence of the sky begins to make a different kind of sense. Part 5. Where is Everybody in 1950? Over lunch at Los Alamos National Laboratory in New Mexico, the physicist Enrico Fermi looked up from his plate at his colleagues and asked a question that science has not finished sitting with in the 7 decades since. Where is everybody? He meant the aliens. The context was a casual conversation about a recent cartoon in The New Yorker, which had depicted flying saucers with a humorous caption. The table included some of the finest physicists in the world, men who had recently helped build a weapon that changed the course of human history, and who spent their lunch breaks making jokes and asking questions about the cosmos. Fermi's question emerged from the conversation naturally, as his questions often did, with the deceptive simplicity that characterized his most penetrating thinking. The logic behind the question is straightforward, and its conclusion is deeply unsettling. The galaxy is at least 13 billion years old. It began forming within a few 100 million years of the Big Bang, assembling itself from collapsing clouds of hydrogen and helium, igniting its first stars, building structure across spans of time that dwarf anything biology has yet produced. Life appeared on Earth within roughly 1 billion years of the planet's formation, possibly within a few 100 million years. If the same chemistry that produced life here is common across the galaxy, and the evidence increasingly suggests it is, then the Milky Way has had billions of years and billions of chances for intelligence to emerge. Some of those chances came before Earth even existed as a solid body. A civilization that arose 5 billion years ago would have had 5 billion years, more than the current age of our entire solar system, to develop technology, to build spacecraft, to expand, to leave traces across the galaxy. And yet, the sky is silent. The solar system is empty. Every radio telescope ever pointed at the sky has returned the same answer. Background noise, natural astrophysical signals, the cosmic microwave background, the hiss of hydrogen and hydroxyl emission, and nothing that bears the signature of intentional origin. Every optical survey has found no anomalous megastructures, no Dyson spheres partially blocking a star's light in a way that no natural process can explain, no laser signals blinking in patterns that carry information. Every probe we have sent through the outer solar system, past Jupiter, past Saturn, into the distant reaches beyond Neptune, has found no artifacts, no dormant machines, no physical evidence of prior visitors. Nothing. This is the Fermi paradox. Not a mathematical contradiction, but an experiential one. The mathematics of probability says there should be something. The sky says there is not. And the distance between those two statements has been generating hypotheses, arguments, and quiet unease among scientists ever since. Dozens of explanations have been proposed. The Great Filter hypothesis suggests that somewhere in the development of a civilization, perhaps in the origin of life itself, perhaps in the emergence of complex multicellular organisms, perhaps in the development of intelligence, perhaps in the mastery of dangerous technologies, there is a barrier so severe that virtually no civilization makes it through. If the filter is behind us, we are almost uniquely lucky to exist. If it is ahead of us, the outlook for our own future may be grim. The zoo hypothesis proposes that advanced civilizations are aware of us and have chosen, by mutual agreement or individual caution, not to make contact, watching from a distance as we develop, waiting for us to reach some threshold they recognize. The dark forest hypothesis, explored in literary form by Chinese author Liu Cixin, proposes that the galaxy is a place of predation, where announcing your presence is dangerous, And every intelligent civilization learns silence as a matter of survival. There are explanations that invoke the rarity of Earth-like conditions, the difficulty of the transition from prokaryotic to eukaryotic life, the improbability of the evolution of eyes or nervous systems or social behavior, the likelihood that technological civilizations destroy themselves through war or environmental catastrophe before they can expand. Each of these explanations addresses the paradox from a different angle. Each has serious advocates. Each has serious critics. But there is one explanation that requires no speculation about psychology or ecology or the internal dynamics of alien societies. An explanation grounded not in what aliens might choose to do or fail to do, but in what the laws of physics permit any civilization to do regardless of what it wants or how advanced it is. They cannot come here. Not because they do not exist, not because they lack the will or the intelligence or the technology, but because the speed of light, the absolute maximum velocity permitted by the universe, is not fast enough to make physical interstellar travel practical across the distances that separate most star systems. And because the energy costs of approaching that speed are so severe that they strain the output of entire civilizations for the delivery of trivial payloads. And because the interstellar environment actively degrades anything that tries to cross it. And because nothing we know of, no physics, no engineering, no cleverness, offers a way around any of these constraints. It is important to distinguish carefully between three things that are frequently conflated in discussions of alien contact, because the conflation leads to persistent confusion. The first is observing another world from a distance. This is easy. Light from Earth radiates outward in all directions at the speed of light. Any civilization with a sufficiently advanced telescope system could in principle detect our planet, analyze the composition of our atmosphere using spectroscopy, and identify the chemical signatures of biological activity. The oxygen that our photosynthesizing organisms pump into the air, the methane that our microbes produce, the nitrous oxide, the exact ratios that cannot be explained by any non-biological geochemistry we know of. A civilization 100 light-years away would see our atmosphere as it was 100 years ago, before we learned to control nuclear energy, when horse-drawn vehicles still shared city streets with the first automobiles. But they could detect us. This requires no travel. It requires only instruments, time, and a telescope pointed in our direction. The second is sending signals. Electromagnetic radiation, radio waves, laser pulses, any form of light, travels at the speed of light. A civilization could broadcast a message toward Earth, and it would arrive, after a delay equal to the distance in light years. This is harder than observation, but achievable, in principle at any distance, provided the signal is powerful enough and directed appropriately. The challenge is the delay. A signal from a civilization 1,000 light-years away would take 1,000 years to reach us. Any reply would take 1,000 years to return. A conversation spanning a single generation is physically impossible with anyone more than perhaps 40 light-years away. The third is physically reaching Earth. Sending matter, a probe, a spacecraft, a living crew, across interstellar space. Carrying mass, accelerating it against the rocket equation's exponential penalty. Shielding it from decades or centuries of interstellar bombardment, and somehow slowing it to a stop at the destination. This is incomparably harder than either observation or signaling. This is specifically what Fermi's question was asking about. Not why they have not called. why they have not come. Consider the mathematics from the perspective of a civilization attempting to reach us. Suppose a civilization exists around a star in the Sagittarius arm of the Milky Way, one of the galaxy's prominent spiral arms, roughly 30,000 light-years from Earth on the other side of the galactic center. They are a mature civilization. They have had 1 billion years of technological development. They have mastered fusion propulsion and can accelerate a large spacecraft to 5% of the speed of light. This is a capability enormously beyond anything we currently possess. 5% of the speed of light is approximately 15,000 kilometers per second. Fast enough to cross the entire diameter of Earth in less than a second. They aim their ship at Earth. The journey takes 600,000 years. Let that number take its full weight. 600,000 years ago, Homo sapiens did not exist. The dominant hominids on Earth were Homo heidelbergensis, a species most people reading this have never heard of. A human relative with a brain somewhat smaller than ours, capable of making tools, and probably fire, living in social groups, but leaving behind no art, no unambiguous language, no symbolic representation of the world. Neanderthals were tens of thousands of years in the future. The divergence between the lineages leading to Neanderthals and to modern humans had not yet occurred. The continents stood in approximately their current positions, but the climate was radically different, cycling through glacial and interglacial periods. Our entire species, every human being who has ever lived, every thought ever thought, every word ever written, every war ever fought, every piece of music ever composed, fits inside a period about 1/40th the length of this hypothetical journey's travel time. If that civilization launched their ship 600,000 years ago, aimed it at where our solar system would be when the ship arrived, it might be approaching now. What are the odds the ship survived? That every system aboard continued to function across 600 millennia of cosmic ray, bombardment, dust grain impacts, and material degradation? What are the odds the civilization itself still exists in recognizable form? What are the odds they maintained the technological infrastructure to communicate with a probe that has been in flight since before our species evolved, to know it is arriving, to care what it finds, to have any continuity of institutional purpose across 600,000 years? These are genuine questions, not rhetorical ones. They are the questions the physics forces us to ask, and they do not have comfortable answers. Now, make the distances more typical. A civilization on the far side of the Milky Way, 90,000 light-years from Earth, attempting to reach us at 10% of light speed. The journey takes 900,000 years. At 50% of light speed, a velocity requiring energy expenditures that would strain even a Type II civilization on the Kardashev scale, one that harnesses the entire energy output of its host star. The journey still takes 180,000 years. Most of the galaxy's stars are separated from us by distances that impose travel times on this order, regardless of how fast we imagine the ship to be. The self-replicating probe concept, sometimes called the von Neumann probe, after the mathematician who first described the theoretical possibility, offers one way to think around this problem. Instead of a single mission with a single spacecraft, imagine a probe that arrives at a star system, uses local resources to manufacture copies of itself, and launches those copies toward neighboring star systems. Each copy does the same. The process repeats exponentially. The mathematics suggest that even at modest speeds, 1 or 2% of the speed of light, such probes could visit every star in the Milky Way within 10 to 100 million years. A short time, relative to the galaxy's 13 billion year age. The difficulties with this model deserve more attention than they typically receive. Self-replicating machines of the complexity required for interstellar travel have never been built. They would need to operate across millions of years, accumulating radiation damage in their computing hardware at every step. They would need to extract and process diverse resources from the varied environments of different star systems, requiring a level of autonomous general intelligence that we have not achieved, and whose reliability across geological timescales cannot be assumed. The exponential growth model assumes no failure at any node in the replication chain, an assumption that biology, the one real example of self-replication we understand, thoroughly undermines. Biological replication is error-prone, and biological systems require billions of years of evolution, plus elaborate error correction machinery to maintain fidelity across time. And even if von Neumann probes could be built and could span the galaxy, their presence would not constitute contact. A machine carrying old instructions from a civilization potentially tens of thousands of light years away is not that civilization. Any communication with its origin would face the same light speed delays. Any response would take tens of thousands of years. The probe would be an artifact, possibly ancient, possibly degraded, present in our solar system but connected to nothing living. What about shortcuts? What about the physics we have not yet discovered? The wormholes and warp drives that appear in the dreams of theoretical physics? General relativity permits mathematical solutions to Einstein's field equations that describe traversable wormholes. Shortcuts through space-time connecting two distant regions without traversing the space between them. If such a thing could be created or found and stabilized, a spacecraft could step from one star to another without crossing the light years. Every known solution describing a traversable wormhole requires exotic matter, a hypothetical substance, with negative energy density, meaning that it has less energy than empty vacuum, a property no observed particle or field possesses. Exotic matter is not forbidden by current theoretical physics, but neither is it supported by any experimental evidence. No exotic matter has ever been detected, produced, or measured. The energy scales required to create or stabilize a traversable wormhole large enough for a spacecraft to pass through are estimated at values comparable to the entire mass energy of a star. The theoretical models consistently indicate that traversable wormholes would be catastrophically unstable, collapsing almost instantaneously unless continuously sustained by exotic matter inputs we cannot produce. The Alcubierre warp drive, proposed in 1994 by Mexican physicist Miguel Alcubierre, describes a different mechanism. A spacecraft enclosed in a bubble of space-time that contracts space in front of it and expands space behind it, moving the bubble, and the spacecraft. Inside, at apparent superluminal speeds without the spacecraft itself exceeding the local speed of light. The idea is elegant. It does not obviously violate special relativity, and the original formulation required exotic matter with negative energy density on the scale of the mass energy of the observable universe to sustain. Subsequent refinements have dramatically reduced the required energy, but all formulations to date still require exotic matter in quantities that have never been produced, and the concept has not been validated by any experiment. It is necessary to be honest about what these proposals represent. They are mathematical possibilities within the framework of general relativity. They are solutions to equations. They tell us that the laws of physics as we currently understand them do not obviously prohibit certain geometries of space-time. They do not tell us that these geometries can be engineered, or that the required materials exist, or that any pathway from concept to working device is available. They are not technologies in any meaningful sense of the word. They are suggestions from the mathematics that the universe might permit something extraordinary, if the universe contains materials and conditions that we have never observed anywhere. There is a version of this argument that always surfaces here, and it deserves a direct response. Surely, a sufficiently advanced civilization could solve these problems. A species 1,000,000 years ahead of us would have physics we cannot imagine. Who are we to say what is possible? This argument contains a subtle but critical error. It conflates engineering barriers with physical barriers. An engineering barrier is something difficult but not forbidden by the laws of nature. Building a fusion power plant is an engineering barrier. Enormously hard, 7 decades of effort not yet fully resolved, but nothing in the structure of the universe prevents it. Given sufficient time and resources, it will be built. A physical barrier is different. It is something the laws of nature prohibit regardless of engineering capability. Traveling faster than light in vacuum is not an engineering problem. It is a consequence of the geometry of space-time as described by special relativity, a theory confirmed by every relevant experiment ever conducted, whose predictions match measurements to more decimal places than any other theory in science. The speed of light is not an obstacle that a cleverer engine can overcome. It is the shape of the universe. An alien civilization 1,000,000 years old would operate in the same universe. Their ships would still have mass. Their physics would still be governed by conservation of energy and conservation of momentum. Their speed of light would still be 299,792 kilometers per second. They might find more efficient ways to approach that limit, but they could not exceed it, and the energy cost of approaching it would still scale as we have described, and the distances of the galaxy would still be what they are. The silence of the sky is not evidence that we are alone. It is evidence of distance. The Fermi paradox may not be a paradox at all. It may simply be the natural consequence of a universe structured so that life can arise on billions of worlds but cannot easily bridge the gulfs between them. A universe where the light speed limit is just fast enough to let you see the other fires burning in the dark, but too slow to let you cross to them in any time frame that civilizations can sustain. A universe that offers observation but withholds contact. That permits knowing but forbids arriving. That opens the sky to your telescopes and then closes every door that leads outside. The galaxy may be full, each civilization asking, in its own language, its own version of the same question. Where is everybody? Right here, impossibly far away, burning their own brief fires on their own small worlds, separated not by silence or indifference, but by the simple, merciless geometry of a universe that never promised us neighbors we could visit. Part 6. The loneliest number. Let us come back now from the distances. Let us come back slowly, the way you come back from a dream that has taken you somewhere enormous. Not all at once, but in layers, the vast spaces folding themselves back into the small familiar dark of the room where you are lying. The ceiling above you, the weight of the blanket or the softness of the pillow, the quiet, the particular quality of the silence in this room at this hour, which is different from every other silence, shaped by the walls and the furniture and the life that has been lived here. We have traveled a long way tonight. We began with a flashlight and a wall, with the comfortable human-scale speed of light that crosses a room in a heartbeat. We moved outward to the moon and the sun, to the ghost star that you would watch for 8 minutes after it had already disappeared. We followed Voyager 1 to the edge of the solar system, and then stepped past it into the real dark, where the distances are measured not in minutes, but in years and decades and centuries and geological epochs. We watched the Tsiolkovsky rocket equation swallow every propulsion concept that tried to outrun it. We watched the deceleration problem double every energy budget and square every mass ratio. We watched interstellar dust turn invisible into lethal at relativistic speeds. Watched cosmic radiation count out the slow damage to any biology that tried to endure the crossing. Watched machines accumulate their inevitable failures across the decades and centuries of a journey no repair crew could tend. And we stood at the center of the Fermi paradox, not as a mystery requiring exotic resolution, but as a consequence. A natural outcome of the universe being the specific shape that it is. A universe where life can arise but cannot easily move. Where intelligence can emerge and look outward with extraordinary clarity and find billions of candidate homes, and still be unable to reach them in any time frame that matters to the civilization doing the looking. This is not a tragic universe. It is an honest one. Here is what we know. The Milky Way contains between 200 and 400 billion stars. Current estimates, based on the statistical analysis of Kepler data and subsequently refined by missions like TESS, the Transiting Exoplanet Survey Satellite, suggest that the vast majority of those stars host planetary systems. Rocky planets in the habitable zones of their stars are common. Not rare, not exceptional, common. There may be 40 billion of them around sun-like stars alone. There may be hundreds of billions when red dwarf stars are included. The galaxy is 13 billion years old. Some of those stars are old enough that any life they host has had billions of years more than we have had to develop, to think, to build, to transmit. The universe has been producing the conditions for chemistry and biology and eventually mind for a very long time. Something is out there. Not probably, not possibly. Statistically, given the numbers involved and the demonstrated ease with which chemistry becomes biology on at least one world we know well, with near certainty. Somewhere in the galaxy, perhaps many somewheres, something is lying in whatever passes for darkness for its species, looking up at whatever passes for a sky, and running calculations that lead to the same conclusion we have been building toward all night. The same recognition of the same wall, the same quiet enormity of the same isolation. They cannot reach us. We cannot reach them. Not because the universe is cruel, not because physics is our enemy, but because the speed of light, 299,792 kilometers per second, the fastest anything has ever moved, is also at the scales the galaxy actually operates on, the loneliest number in physics, the number that keeps everything separated, the number that lets you see but not touch, know but not visit, imagine but not arrive. There is a version of this truth that is bleak. That frames the cosmos as a prison. Billions of fires burning in billions of small rooms with no corridors between them. No way to cross from one warmth to another. Each civilization sealed inside its own small corner of an enormous dark. And then there is another version. The same truth, the same numbers, but held differently. Think about what the speed of light actually is, from the perspective of the being who first measured it. Ole Romer, watching the moons of Jupiter from a 17th century observatory in Paris, noticing a tiny inconsistency in the timing of eclipses, and understanding, correctly, that the inconsistency was caused by light needing time to cross the changing distance between worlds. He was measuring something that had existed since the universe began, a constant woven into the fabric of space-time before the first star ignited. The speed at which all electromagnetic information propagates, the speed at which the universe communicates with itself. Every photon that has ever reached your eye has crossed some part of the cosmos to find you. The sunlight on your face carries the story of a nuclear reaction 150 million kilometers away. The light from a distant galaxy in a telescope photograph has been traveling for billions of years, longer than Earth has existed. Every image you have ever seen of a nebula, of a cluster of young stars, of the swirling face of a spiral galaxy, is a message delivered at 299,792 kilometers per second across time and space to arrive at precisely the place and moment where you received it. The same speed that isolates us is also the only thread connecting us to everything. Every civilization in this galaxy, every world where something has learned to look up, sees the same stars. Not the same as we see them. The parallax is different from each vantage point. The distances vary. The constellations are unique to each observer. But the same objects. The same burning spheres of plasma, the same nebula, the same galactic structure, the same ancient light traveling at the same absolute limit through the same fundamental dark. We are all reading the same book from different pages. You are made of atoms forged in the hearts of stars. This is not a metaphor, it is chemistry. The carbon in your cells was not present in the early universe, which consisted almost entirely of hydrogen and helium. Carbon is produced by nuclear fusion in stellar cores, in a process called the triple alpha reaction. 3 helium nuclei colliding and fusing into carbon-12 at temperatures above 100 million degrees Celsius. Every carbon atom in your body was synthesized in a stellar core, a process that took place billions of years ago in a star that no longer exists. When that star died, either in a quiet exhalation of its outer layers into a planetary nebula or in the violent detonation of a supernova, those carbon atoms were scattered outward into the interstellar medium. They drifted. They were incorporated into new clouds of gas and dust. Eventually, some of them found their way into the disk of material orbiting a young star in the outer spiral arm of the Milky Way. That star is our sun. That disk became our solar system. Those atoms became, among other things, you. The iron in your blood was forged in supernova explosions, the only sites in the universe where iron can be produced in quantity. The calcium in your bones was synthesized in the late stages of massive stellar evolution. The oxygen you are breathing in this moment was produced by stellar nucleosynthesis across billions of years, and scattered by stellar winds and explosions across the interstellar medium until it reached this atmosphere. You are not merely in the cosmos. You are made of it. You are a temporary arrangement of ancient stellar material, briefly capable of awareness, lying in a quiet room, thinking about the size of the place it came from. The atoms in your brain that are producing this thought have been inside dying stars. They have drifted through the interstellar medium for billions of years. They have been part of countless other structures, other molecules, other compounds, other organisms, perhaps, before they found their way into the configuration that is you, right now, in this room, at this hour. Every atom in your body carries the record of a universe 13.8 billion years old. Let that thought spread through you slowly. Feel where the weight of the day has gathered, in the shoulders maybe, or the jaw, or the small of the back, or behind the eyes. The specific places where tension has pooled through the hours you have been awake. Breathe toward those places. Not a forceful breath, a slow one. The kind of breath you take when you have put something down that you have been carrying too long. Let the expansion of your lungs remind you that you are here. Specifically here, specifically now. In a body that has traveled 4.5 billion years of planetary history to be lying in exactly this spot. The universe is very large. You are very small. Both of these things are completely true, and neither of them is a cause for fear. The smallness is not a diminishment. It is a context. A candle in a very dark room is still a candle. It still burns. Its light still reaches every surface it can find. The size of the room does not change what the candle is. Somewhere in this galaxy, other candles are burning. They cannot reach us. We cannot reach them. The light years between us are real, and they are permanent, and they are not going anywhere. The loneliest number in physics will remain what it is, and the islands will remain islands, and the ocean of space-time between them will remain the width that it is. But the light still moves. It moves in every direction, from every fire, at every moment. It crosses the dark. It arrives. It carries the news of what was, and, sometimes, in the faintest hypothetical, the news of what is thinking. In whatever form thinking takes on a world orbiting another star, asking the same question. Tonight, beneath whatever skies above the place where you are listening, that light is moving. It has been moving since long before you were born, since before your parents were born, since before any human being had looked up at the night sky and wondered, since before there was a night sky to look up at, before the sun existed, before the earth condensed from the scattered remnants of a dead star. The speed of light is 299,792 kilometers per second. It is the wall between civilizations. It is also the only connection we have to all of them, to all those distant fires, to all those ancient suns, to all those worlds where something, perhaps, is lying quietly in whatever passes for dark, and wondering what is out there, and whether anyone else is wondering the same thing. We are. Breathe slowly. Feel the stillness around you. You are connected by light to everything. Where are you listening from tonight? Wishing you a peaceful night beneath the stars.